Hello and welcome back to Calculus 1, section 3.9, derivatives of exponential functions and logarithmic functions. See, there's no energy, it's just, yeah. So let's deal with exponential functions first. We have already, I hope we have the knowledge that the derivative of e to the x is e to the x. Now there is a proof that you can do using the limit definition for it, which is the one with the difference quotient, right? So you can do that if you want. You would have to know the limit of e in order to do it, though. We also covered the one that chain rule deals with, which is the hold on, pen died. I still have the battery in it. That is good. Just have to shake the ink. There we go. You shake the ink, it starts. So it's a Microsoft product. You just restart. Even if it's dead and stomped out and the parts are lying in like 3 different galaxies, you just restart and it's going to work. It's like Russian equipment, okay? Apple stuff, it coughs. Just throw it away and spend another $3,000 for the same garbage. Oh, huh. Took me 3 months to get this. So it was always sold out. I didn't want this color though. Anyway. So, oh, and if you want the picture with me, like, you know, for social media or whatever, it's a fundraiser for Rotaract, so $5. So we have these 2 exponential functions, and we know these derivatives from previous lectures. Today, I'm just going to give a more general case, because we want to incorporate the chain rule. And then we also want to make it so general that it's not just base of e, but base with any number, like 2 or 7, right? And those will greatly help us, you know, when we need them. So let's go first with the chain rule component on e to the x, right? You say e to the f of x. So that could be e to any function you can possibly imagine. That function could be sine x, could be x squared minus 3, so whatever you can come up, it doesn't matter. Whatever you can come up with. The derivative would be e to the f of x times f of x prime. And we know this because it's just a basic chain rule. There's nothing special about this formula. So what would be the most general case that we can write, right? What would be the formula that takes care of all exponential functions ever? That would be the derivative of b to the f of x. So now you are allowed to have any number in a base, right, including fractions, including positive, negative number, whatever. And then you are going to have whatever function in the exponent. So you cannot have a more general case than this. This is it, right? What is the derivative? The derivative is going to be b f of x times f prime of x times ln b. Now this is the one that is getting boxed. because this is the formula for exponential. Anything that we have is the part of that formula. So let's take a look if this formula would actually fit e to the x as we know it. Well, if we are taking the... Hold on. If we are taking the derivative of e to the x and we want to use the formula up there, we see that b is equal to e and our f of x is equal to x. So now, with the knowledge of these things, we just compile the other side. So b is e, f of x is x, times the derivative of f of x is 1, and ln of b would be ln of e is 1, and we just get e to the x. Yay, right? So it works. The formula does work, right? So this is the most general case. Now, obviously, we're not going to use it to figure out the derivative of e to the x or the derivative of e to the ax or any of those things, because we know that e to the x is easy to deal with. I have a funny story about that. 2 years ago, a student in Calc 3 protested during the exam that there are too many freaking e's. That was the exact wording he used. And then left the classroom about 15-20 minutes before the exam ended, because a lot of problems had derivatives and integrals of e's. The next class didn't show. The following class showed up and complained again. So another student stood up and said, "Dude, shut up. E's are easy to integrate and differentiate." And that was the end of it. So yeah, E is easy to differentiate and integrate. So you are actually hoping to see that function as much as possible, because the derivative of e to the x is e to the x. Yeah, zero effort there, right? Like x squared you have to change from quadratic to linear function, so yeah, there's mental process there, right? For e to the x, just Control C, Control V, and that's it. All right. Let's see what is the derivative using the formula above of 2 to the sine x. All right? That's your job now. Okay, so b is 2, f of x is sine x. So we have, well, I mean, with exponential functions, you always have Control C, Control V on the first part, right? Copy as is. And then the derivative of sine is cosine x, and then times ln 2. Nothing factors, nothing, right? So you just have to leave it as is and then move along with your life. Can you set this equal to 0 in chapter 4 and solve? Yes, right? The answer you're going to get is pi over 2, right? This is a constant, has no solution. E to the x, or any exponential function, doesn't cut through x-axis, so that has no solution. So the only part that would give you a solution is cosine x equal to 0, and that gives you pi over 2, so there you go, right? Before you freak out, just, each one of these gets set to 0 using the what we call zero product rule. So that's a chapter 4 talk already. Another derivative, which is 1/3 raised to x squared plus x minus 2. All right, so b is 1/3. Now what you could do is you can make that a 3 and then put minus in exponent and change all the signs, but it will be overkill. So copy exponential part as is times the derivative of the exponent, which is 2x plus 1, times ln of 1/3. And that's it. So this is going to end the story of exponential functions. You will be paying attention to this derivative formula that is general, but about 99% of the time in your life, this is the formula to use, right? Because most of the application we have is e to the x based. Very few have like stuff with waves. If you deal with decibels, like sound intensity, earthquakes, pH values in chemistry, like they would have base 10. application. But vast majority of other things that we deal with will all be base E in sciences. So, you know, as I said, maybe I'm going to box this one as well. So this is like 99% of the time, this is the formula you use right here. Use this 99% of the time. There we go. Great. Now we go to the next. Can I pull this off? I don't know. It's going to look weird, right? What is this? It's a log. Nice. Perfect. All right. I still got it. I still got it. All right. Logs. So I was waiting for the artist's reaction, but it was just, yeah. Probably that's pretty good. It was pretty good. First, let's talk about logs in general before we go and do derivatives of logs. Just notice that I haven't done this over here. No coffee. Much better. So let's start here. 2 plus 3 is 5. And then I can subtract 3 to get 2, and I can subtract 2 to get 3. So I'm able to retrieve these input numbers, if you will, right? 2 and 3. I'm able to retrieve those using the opposite operation of subtraction. Let's raise the stakes now. What is 2 times 3? 6. Now, 6 divided by 3 is 2, and 6 divided by 2 is 3. Great. So multiplication is defined as the fast repeated addition. Now, we can actually do fast repeated multiplication by working out the exponents. So what is 2 cubed? 8, right? And if I want to undo this, the cube root of 8 is 2. How do I retrieve 3? I can't do square root of 8 because that will be just 2 root 2. That's not 3. How do I retrieve 3? There has to be a way so we can complete this chart. I mean, the whole mathematics would be garbage if we couldn't do that. Because mathematics likes to be complete. Anyone? How would I retrieve 3? Combining 8 and 2 somehow.
Wow.
Thank you. A log. Very good. Log base 2 of 8 is 3. So what is log? Logarithms, is just a mathematical operation, like addition and subtraction. It's no different than any of them. It's you combine two numbers with mathematical operation called log. And just the poor thing is so unfortunate it has letters instead of a cute symbol that you immediately discriminate against it, right? Because you're terrible people, obviously. So it's just a calculation. Log is not a function. It's operation that is placed between two numbers to produce a third number, just like anything else on the list. And you see it over there at work, that if you combine 2 and 8 with the log, you get 3 on the other end. And we can do that over and over and over again. So I can combine log 3 and 81 and get 4 on the other end. I can combine log 5 and 125 and get 3, right? I can go log 10 of 100,000, right, and get 5 on the other side. So logs just compute numbers. So we know that 3 plus 81 is equal to 84. We know that 3 times 81 is 243, right? So we have these operations, but see, the trick is that you dealt with all of those calculations since grade 1. And you have 12 years of experience. And then here comes poor log 10 years later, I'm operation 2. And you just go, nope. Too late, buddy. If you showed up in a first grade with all the rest of operations, right, that we took care of by grade 3, you might be in our little circle of chosen people, right? Now, since you're so different that you have letters instead of a cute symbol, we don't like you. Like, wake up that social warrior in you, right? Social justice warrior. And invite log, right, in the circle, right? Because maybe log has something to say, to give a positive contribution to everything, right? All right, now, we understand, hopefully, that log just computes numbers. That's the end of the story. And then, the same way that you would take addition or multiplication and create functions by introducing variable x, you are going to create a function of a log by introducing x. So logs have nothing to do with functions. Logs, that's its operation. And then we put in x. So if we had earlier 3 plus 2, and now you're saying 3 plus x, well, that's a function because now you have 3 plus x there. The same thing, you had 3 times 2, and then you have 3x, that one is a function. If you had log base 2 of 8, and now you're writing log base 2 of x, that one is a function. So we have a function in this case. So what I'm going to do now is I'm going to introduce the idea of just the basic properties of log, right? So I have a log of y equals log base a of x. And then I would like to know what types of functions would satisfy this, what type of a function would satisfy this creature. So we have the graph for the log, which goes through number 1, has the vertical asymptote at x equals to 0. It is always increasing function. The domain is positive numbers. We are excluding 0. Range is all real numbers, so we can just put double bar r, or you can put negative infinity to positive infinity. We have the x-intercept to be at 1, 0. We have no y-intercept. There is the vertical asymptote at x equals 0. Function is increasing. Function is continuous. Function has an inverse. So all of these specs that you actually learn in your pre-Calculus 1 course, these are the specifications for logarithmic function. Then we have some of these cute formulas and properties that logs have. you know that some functions are more advanced than others. So for polynomials, you practically can add them, multiply them, and yeah, right. But for trigonometric functions, you have all the identities, and then you have some stuff for logs as well. So let's see what are the things that are cool for logs. First of all, this is not going to be useful for us in this class, but the most important thing for logs is that it's inverse of exponential function. So what we know as a conversion formula, you might use it this semester to solve some equations, but we are not using this to take any derivatives or integrals or anything like that. So conversion is the most important formula, and that is that a to the b equals c converts into log base a of c is b. So this is the most important formula that you would write for logs. And now, if you take a look at your calculators generally have the LOG button or LN button. Vast majority of the calculators doesn't have this situation where you can plug in anything, right? So in order for us to be able to use this, we would have to know something is called change of base. But before I go into change of base, we need two life improvement formulas. That's what I call them. So the first one is that, like the quality of life. That's what I want to say. Quality of life formulas. There we go. So the first quality of life formula is that if you have log x, what that means is the log base 10 of x. So a lot of applications out there, and I named some earlier, like pH value in chemistry, and then waves and earthquakes and sound intensity and so on, they actually have base 10. And since it's used in sciences and it's frequent, if you see no base, it's implied that base is 10. It's just like when you see no operation, you know the implied operation is multiplication, right? Because you can write 3x plus 1. So you didn't put times. It's assumed that between 3 and the parentheses is multiplication. So the same thing goes for logs. If there is no base, it's 10, okay? And then the next one is ln x. This is log base e of x. So there is no, it's nothing special about ln. It's just a lazy notation, okay? It's 2 characters shorter than the other one. That's as simple as that. So this one has 3 characters, the other one has 5. It's 2 characters shorter. So if you have to write, you know, ln x 10 times, you just saved 20 characters, which is a quality of life improvement, right? That's what it is. So these are the quality of life formulas. So now we can finally get into the change of base formula, and the change of base formula is the one that helps you use the calculator to compute logs on the daily basis, as you compute logs on daily basis, right? Are you computing logs? Yeah. You should memorize some of the odd logs. Like, memorize like first 4 digits of like log of 7.9, so that you can annoy people when they go, what do you know? I know log 7.3 to 4 decimal places. What do you know? Oh, it works so great. This is why no one talks to me. They just say Nick is right by default. No debates. And yeah, because especially if they add, I have kids. Like, what do you know? I have kids. Oh, really? Like, there is a PhD in having kids now. So it's like, yeah, perfect. Like, do the 2-year research before, yeah. Right? So here we go. Change of base. So any log, right, any base and any number will be dealt by log b over log a, note that that's base 10, or ln b over ln a. You pick, right? Your calculator will have one or the other or both. Now, there are some scientific calculators that would have log a, b, and then you can type these values in. But those calculators are very rare. So all of the graphic calculators, your TI 83, 4, 6, whatever, none of them have log AB. They just have a capital LOG. So this button over here would be capital LOG on the calculator. And this one over here would be capital LN. So those are the buttons that you have on most of the calculators. Again, if you have the right technology, you can install these calculators for free. If you have the Apple garbage phones, throw them away and get the real phones, and then you can do this, right? And many other things. You would be amazed at what you can do just by how much your life would be better and horizons broadened and everything else. As soon as you give up on that. All right, so that's the change of base formula and the conversion formula. Again, none of these will be used in our class because we don't necessarily solve equations and calculate logs in this class. Now, the formulas that we are going to use in this class and that you must know are the three formulas that I'm going to write right now. So number one, log of any base of x times y is log ax plus log a y. Number two, log any base of x over y is log ax, common sense, minus log a y. So multiplication goes into addition of logs, and division in the argument goes into subtraction of two logs. And finally, we have number three, log of any base of x to the power p. P gets kicked in front of the log, and just have log a of x. So these three formulas together, nice. Will be a good effort. Maybe I should, yeah, I'm going to change to that now. Just say congratulations for some time. But good effort is better, right? So these formulas here will be used extensively. Remember how I said if you want to, be really godly in taking derivatives mentally and skipping technically the rest of the chapter 3, you have to be able to mentally shovel these formulas in your head. So that's the part of you, getting to that sentinel level of, derivative taking. I should make that meme, actually. Yeah, okay. Just trying to get all 5 levels to fit, and I think all right, fine. That's my homework. You have to do quizzes. Life is never fair, right? All right, so let's talk finally about calculus of logarithmic functions. We are going to deal only with, obviously, with derivatives, and then eventually the integration of logarithmic functions is all the way in Calc 2, so you can do the for now, and then you can scream later. It's called procrastination. So here we go. The derivative of ln x is 1 over x. This is the most basic formula that it's in existence, and pretty much you are going to use this about 2% of the time in your life, all right? Because generally nothing is modeled by ln x. What you are going to use about 99% of your life is ln of f of x. And that is the most important. It's not the most general formula, just like for e to the x. It's not the most general formula, but it's the one that it's mostly used across the board. And that one would say the derivative of ln of f of x. So now you have whatever function there. Now this is how easy it is. Take the argument as is and copy it in the denominator. So f of x. And put its derivative on top. That's it. That's all it is. So this is the formula. Need to make sure you see this prime over here. So this is the formula that you will be using most of the time. Use this most of the time. Like 99% of the time, that's the formula. So now, I'm going to write the most general case. And the most general case for this derivative would be any base. Remember that ln is base e, right? So now I want to write the most general case of the derivative of log base b of f of x. So now your base is not e any longer, could be anything else, and then your function, again, is any function. So we are going to have the same thing, and then we are also going to have ln b. So the same component of f prime over f as is, and then just times ln of the base. So this is the most general case, and you'll probably use it twice in the example that I'm going to give you, and then in one of the exam questions, and that's it. I don't see people use this rule ever, because most of our application is ln up there. So let's go with the derivative of ln of x squared minus x plus 2. So it's as simple as this. Take the function in the argument and write it down and put its derivative on top and walk away. That's all it is. Done. Let's do another one. So the derivative of ln of e to the sine x. What's the answer?
E to the x cosine over e sine x.
What was the top?
Oh, e to the cosine of x? I put e x cosine.
You have to keep the same exponent. So e to the sine x, yes.
That's for the top.
That's for the top.
Yeah, e to the sine x times cosine x.
Oh,
Cosine,
Oh,
yeah.
okay.
Cosine is in chain, right? And then e to the sine x and e to the sine x cancel, and you get what? Exactly, because ln and e cancel, and you just get the derivative of sine, which is cosine. Good. Right? Right. Good. And now, grand finale. I wish there was much more records than that. For the grand finale, we can do, I don't know, something like that. Or not in this class, obviously, but yeah. If it was my Calc 3 crew, then obviously, yeah. When I say grand finale, it's like chaos for 30 minutes. So I'm not saying those words in that class. So, logarithmic differentiation. I'm not sure if any one of you attempted the problem from yesterday that I told you that you can, play with in about 30, 40 minutes, right? Say the question is to take the derivative of cube root of x squared plus 3 divided by x to the 6 sine x, right? Or even better, sine squared x. How about that? So, what do we have? Well, we clearly have a quotient rule with the chain rule with the cube root, the chain rule with the sine squared, the product rule between x to the 6 and sine squared. right? So you have two chains embedded, one of those in the product, and then product within the quotient. And yeah, this will take a very long time to do using what you know from your chain rule section from yesterday. We did spicier problems. If you missed it, make sure you watch the part 2, which is where most of the problems actually are in Calculus 1, 2, and 3, and differential equations, and so on. Now, how do you take derivative of this? Well, as I promised yesterday, you just write out the solution. You don't, go through all of the quotient rules and product rules because it's just too long, and we like instant gratification. So you look at any derivative, and without doing any steps or anything, you just write the solution out. So that's that. It is simply obtained like this. So you just write cube root of x squared plus 3 divided by x to the 6 sine squared x times, and now you have 1/3 x squared plus 3 times 2x minus 6 over x minus 2 cotangent x. There, done. So when you see a derivative that it's very, very complicated, you just write the answer and you move on, technically. And that goes for any derivative we ever had prior to this point. So this is the power of logarithmic differentiation. It allows you to skip everything you learned in chapter 3 by combining two concepts. One are those log formulas, and the other one is that log ln f of x derivative that I told you you're going to use most of the time. If you know those two components, the rest of the derivative is right. You will never have to do another chain rule, product rule, quotient rule, or anything like that. Plus, you see, it's just you take it mentally and you just write, and it's in factored form already, right? So there's that plus, right? It's great. So how does this work? Well, let's do a vanilla example to explain the process behind, and then as you do 5 million of these problems, if you're interested, obviously, you will pick up the pattern and you will just be flying through all derivatives out there. So I know some of you will probably kill the weekend to learn this, but this is the most powerful derivative taking technique in the galaxy. So let's see. Let's do something simple to just get used to this stuff. So how about sine x over x cubed? I know you're supposed to do quotient rule, but yeah. Right, this is the question. So here's what you're going to do. You create y equals sine x over x cubed. Then you put in the log on both sides. I mean ln, not the log I drew previously. And then you expand the right-hand side. Now division goes into subtraction of logs, and then the exponent 3 goes in front. So this is ln of sine x minus 3 ln x. Use properties of logs, and properties of logs are listed right here, guys, in this list. So you see that I had sine divided by x cubed, that's the minus, and then that cube was that p that goes in front of the, right? So I used rule 2 and rule 3 in this case to break this apart. Now, that's the part that you have to be able to do mentally. The rest of the problem is a joke. So if you're able to decompose this through logs mentally, now it's time for you to take the derivative. On the left-hand side, the derivative of ln y is 1 over y. dy dx, if you remember your implicit differentiation, you were taking the derivative of y in respect to x, so you have to follow with a chain. On the right-hand side, you are taking joke derivatives. It's ln derivatives. Write the function as is on the bottom, which is sine x, and put its derivative on top, which is cosine x. Minus 3, you copy that, and it's 1 over x for the derivative of ln. Do you see how the only thing that is left for me is to multiply y to the other side, and that y is the original problem? That's the reason why I copied the original problem here when I started writing the solution mentally. All I did to solve this insane problem, the derivative of this in my head, was to say, okay, I know that I have to copy this because every time if I do the entire procedure, I will always get 1 over y on this side, and that goes to the other side, which is this. So you start by copying that piece. And then in my head, all I was doing is I was decomposing this using log rules. Exponent of 1/3. Exponent of 1/3 is the p that goes in front of ln. Copy the function in denominator and its derivative on top because it's f prime over f. This one is in denominator, so minus. The exponent goes in front of ln, and I have ln of x. ln of x is 1 over x times the 6 in front, so 6 over x. This one is also in denominator, right? You don't have to do this in your head. I'm just saying that it doesn't matter how complicated the problem is. This is like those sophisticated martial arts, you know? They say, the more opponents you have, the better, because you can use their momentum and their energy against them, right? Yeah, right here, right? The crazier it looks, it's more intimidating, right, for noobs, but for us, right? Not a problem, right? And the last piece is a little bit tricky because sine goes in denominator, its derivative cosine on top, cosine over sine is cotangent. So sure, yeah, make it into 2 steps, I don't care. But with sufficient practice, right? I mean, everyone had, I mean, not me obviously, but people have to learn this, right? And then you become good. I was born. So now I moved y to the other side, and this becomes cotangent x minus 3 over x, and then I just write in what y is, and the problem is solved. So that is logarithmic differentiation. And as I said, you can literally go back in your notes and apply this method to every single derivative we did. And it would be a one-liner if you know how to do it in one line. I will go through this procedure again. It really doesn't. The only one that gets to be a little bit tricky is if you have one of the e's show up, because they cancel, right? That's the only ln of e cancels, as I had in the previous example. We'll do one of those as well. But if you have any other function, then it's just joke. You plow through it. All right. Let's get a student-made function. So let's get something in the numerator. Let's get some function. What should we put there? Just say anything, whatever. Doesn't matter. X squared plus 9. You went all out. I'm going to put that to the 6th power. And then what should we put in denominator? E to the cotangent. I like that. E to the cotangent x. Keep talking. Let's put one more thing here. Times 2. Can we have a function that has some weight to it? Times what? We got the polynomial, we got the exponential, we got the trigonometric function, so how about we get some root of some order of something? You look like you want to say something. Yeah.
Third root of x.
Okay, what I heard is third root of x to the 12 minus 6.
Yeah, exactly.
All right, great. Let's unleash the procedure. We start with y equals, leave some space to fit in log. We have x squared plus 9 to the 6th power. Then we have e to the cotangent x, very good contribution, I like it, times cube root of x12 minus 6. This should be your next problem when someone says, what do you know? I can take derivative of this mentally. And the follow-up, obviously, and I don't even think you can spell the derivative. So we're going to put ln now. Left-hand side, nothing to do. Right-hand side, all the expansion is there. The top, 6 goes in front of ln, and we just have x squared plus 9. Easy, right? Minus cotangent x is the exponent, so that goes in front, and then we have ln e. That cancels to 1, so we'll actually be ignoring that part. Minus again. Now you will say, wait, it's multiplication. Yeah, it's multiplication, but it's in denominator, so it's actually a division. So minus, cube root is 1/3, and then by popular demand, x to the 12 minus 6. Oops, I forgot the ln. Beautiful. Time to hit this with the derivative dx. On the left-hand side, as always, 100% of the time, 1 over y, dy dx, which is the reason why we always have original function times the rest. All right, let's go to the derivatives over here. What do I have? 6 times. We have x squared plus 9 in denominator and its derivative on top. All right, no ln in the next term. The derivative of cotangent is very good. It's negative cosecant squared, and then negative and negative make positive. Minus 1/3. Copy the x to the 12 minus 6 in denominator and put 12x to 11 in the numerator as the derivative. So now, to avoid writing 50,000 steps, the y will go to the other side and I will plug in at the same time. So I have dy dx is equal to, and now I have the good old x squared plus 9 to the 6 divided by e to the cotangent x, cube root of x to the 12 minus 6 times the parenthesis. I have 12x over x squared plus 9 plus cosecant squared x, and then 1/3 and 12 cancel, minus 4x to 11 divided by x 12 minus 6. There's your derivative. Guess what? You can find the tangent line from here. Just imagine, or even better, go home and try to take that derivative by hand, right, using the product rule, quotient rule. You'll be absolutely insanity. And what I am telling you guys is that by Monday, if you invest enough time into breaking down functions with those log rules and you know, decomposing that stuff, expanding actually, and then remembering that simple derivative of ln is you copy the argument in the bottom and put its derivative on top, you should be able by Monday, I would say, to take these derivatives mentally. But definitely by the exam, right? Now the exam is going to say, use the product rule to find the derivative of. Use the quotient rule to find the derivative of. And you use those rules and you show the steps for partial credit if you mess up and all of that kind of stuff. But then those of you who actually invest time and effort into learning the procedure for this, you can quickly mentally check all of your work, right? Because you would be so powerful at that point, right? Right? All of those noob techniques, you don't need them anymore. Like the product rule and quotient rule and stuff. Because, right? Now, obviously, you will need to know them because exams will clearly state, do those because that's the assessment of, that's the assessment part. Well, we're going to go over a break, and then when we come back, we have one more section. Just want to make sure that you know that the tangent line problem is just fine. This is just a derivative taking technique, right? So once you have the derivative, now you want to find the tangent line at x equals 1. Yeah, go ahead, plug in 1 everywhere, and then figure out that the slope is, I don't know, 3.6. And then you will use that and, right, the rest of the stuff to find, So this is logarithmic differentiation. Tons of problems in the book to practice, but technically, guys, now you can take the derivative of anything you write down. And you can always ask software to check your work. Or you can type this in Wolfram Alpha or whatever else you're using to check. So, about 5 minutes and we restart. Bye-bye.